Hello, everyone. I'm very pleased I can welcome our next speaker of today's part of Prague seminar for mathematical physics. And he's Fridrich Valach from Imperial College in London. And he decided to give us some hot news from type II superstrings and exceptional Algebroid stuff. So, the stage is yours.
Thank you. So thank you very much for the introduction, and thank you also very much for giving me the opportunity to talk to you about this wonderful project that we've been working on. So this is a joint work, I should say, with Mark back then, Ondra Hulik, and Dan Waldron. And most of it can be found in the two papers which are on archive, and some of them yet to come. So some of you, or maybe even most of you, remember that I gave a similar. Well, I gave a related talk in spring, maybe on a related topic. So this thing will be. There will be some overlap. I mean, there is no knowledge assumed of the previous talk. I will, but yeah. So in some sense that talk was related to M theory, and this one will be related to type II superstrings. So I will explain what these things mean, and like some of these buzzwords will be explained. So let me, and the emphasis will be on type II string theory or superstring theory. So let me start in a similar way the abstract was written. So let me start with talking about particles. Okay, I mean that's not how it was written in the abstract, but anyway. So just to give you some sort of analogy. So by particles I mean GR, which is of course not the same, but okay, I mean okay, so if you have, so in general relativity you have a manifold and you have a metric on it. So this metric is usually Lorentzian, but here for simplicity, I mean, yeah, here for simplicity, let's assume that it's Riemannian. There are not much changes in the story. And yeah, so this is the space-time. It can be curved, you know, because it's a metric, whatever. It can be interesting. And then if you put particles on it, then particles move along geodesics. And this background itself suddenly has some equations of motion which tell you how it well evolves or whatever. There's a constraint on the form of this thing, and the constraint is given in the form of Einstein's equations, which in the vacuum they have the form, the Ricci tensor corresponding to the metric vanishes. So yeah, that's all I wanted to say about particles. Now let's go to strings. But before that, I will add one more bit of reformulation here. So what is which will be useful in the other viewpoint. So the metric here, one way to look at it is that you have a so related to this manifold, there is a sort of natural object which is the tangent bundle, and the tangent bundle has a GLN structure. So I mean which sort of an empty statement. I mean it just, well, the structure group of this is GLN, and if you reduce the structure group down to, maybe wobbly line is better, down to the maximal compact subgroup of that, which is ON, then that corresponds to choosing a metric, okay? Because such a reduction tells you that you are singling out some sort of frames which you declare them to be orthonormal. So equivalently, you can say that there is this bundle with this structure group, and choosing a metric corresponds to choosing a reduction of the structure group. I mean, reducing the structure group to ON. And this viewpoint will be used also for the other, in the other cases. This thing here. Okay, so now let me go maybe to, okay, I don't know how useful it is to use this wild choice of colors, but okay, let me do that. So if you have strings, now I want to go one layer higher in the hierarchy. So for strings, you again have some sort of space-time manifold where the strings propagate, and this can be, in first approximation, it's given by a metric, but there is more. I will fill in what more means, but and in this you can imagine, at least to some degree of usefulness, that there is some strings propagating in it which form some two-dimensional surfaces or some submanifolds of this M. And if there would be just a metric, then usually the classical trajectories would be similar to geodesics in particles, which would mean that you have some extremal surfaces. Okay, but anyway, what we're more interested in at this point is that this background again satisfies some equations of motion, or it has some constraints on it, such as here it was vanishing of the Ricci tensor. So if this would be all, then in the string case you would also have just the same equation. But strings have there is a richer background in the case of string theory, and that is okay. So in order to talk about that, so let me say that there is various flavors of strings. So you have so the simplest one is the bosonic string, which is kind of, well, bosonic. So there is no fermions, and it has some problems by itself, but let me not talk into that. And in that case, if you have that case, then the background is formed by the massless fields that appear in string theory, and those are the graviton or the metric. Then there is a let me call it the B field. So this is some two form on M, and there is some scalar field, which is so this is just a function on M, and this would be all as far as the massless sector is concerned. There is also the tachyon here, which causes some problems, but let me ignore that. And and again, in this case, you have there is a nice way to write these kind of equations. So there is a set of equations that governs this background, and I'm not going to write them because there is a better way to write them, and that better way is in the following way. So you associated to this manifold, now you construct what is called the generalized tangent bundle. So let me also maybe say, for those who know, that I will be working mostly just locally, so I will not be concerned with cohomologies and things like this, at least for now. So suppose that you, instead of this guy, you take this guy. Now if you have this other guy, then this thing has a natural pairing. So there is an inner product of split signature of this guy, which consists of pairing vectors and covectors. So if you have two vectors, then the inner product is 0. Two covectors, it's 0. But if you have vector covector, the inner product is given by the pairing. And that thing actually, so this thing equips this guy with an inner product. And in other words, there is an ONN structure. And now my claim is that you can actually encode these two fields together by saying that you want to now reduce this structure group down to its maximal compact, which is ON times ON. And so roughly how does this go? So I will draw some picture now. So suppose that you have this T plus T star, so at any point. Hopefully this is visible. This chalk is very bright, so maybe, okay, let me maybe use a different chalk color, this one, okay. So if this is your T plus T star, now going down, reducing this down to ON times ON basically corresponds to taking two orthogonal subspaces, which we can call V plus and V minus. And then these small groups will then just correspond to rotations, to orthogonal transformations of these two planes, or these two subspaces independently. So you rotate one of them and you rotate the other one. And so, and since this is just the orthogonal complement of this guy. So basically what I'm saying here is that such a thing you can see there's a choice of this subspace, and this subspace, and as a next step, this subspace so now we can forget about V minus, because that is determined by V plus. So, and this V plus you can now encode in terms of you can see it as a graph of a map from T to T star. So this is a graph of some map, let's call it E, from T to T star, but that is nothing else than such an object. That's the same as saying that you have a tensor of this form. So it's a element of this tensor product of T star with itself. And such a thing has a symmetric and a skew symmetric part, and that precisely corresponds to taking the metric and the B field. So, okay, so this was a rough sketch of how this goes. And Yeah, and then there is the dilaton, which is kind of a more subtle issue. There is a way how to do that, how to kind of put it in the generalized metric, but let me not do that. Let me get to it maybe later. But the point here is that, again, so the equations of motion for this background, they can again be written in some form that there is some generalized Ricci tensor. So there is a natural object that you can build out of this V plus. But as opposed to the case here, this generalized Ricci is not is ambiguous. There is some ambiguity in its definition, and so one has to fix this ambiguity in some way. And so one way to do that is to, or actually the way to do that is to use the dilaton. So actually you need to use the dilaton to fix the ambiguity, and then the equations of motion are just this and the vanishing of a associate of some sort of scalar curvature. So these are the equations of motion, and they can be neatly written in this V. Oh, sorry, here I denoted these two guys together by V plus, which is this. Okay, just to have a shorthand notation. Yeah, in the previous case, vanishing of the Ricci would imply vanishing of the scalar curvature, but in this case, this is more subtle and it's different. Okay, so here I should say that this is based on works of many people. So there is for instance, there is Coimbra, Strickland, Constable, and Waldram. There is also Braño and Honza, and Mario Garcia Fernandez as well. And that one will be concerned with the heterotic case, to which I will go now. In particular, probably should say Marco Gualtieri as well. Yes, probably that was. Yeah, so many people, and Pavel and me also did a bit of work about something that I will discuss soon. So, right. So much for the bosonic string. So now there is different kinds of string theories which are perhaps more physical. So, for instance, there is the heterotext string, or heterotext superstrings. So. But even though all of these are superstrings, except for this case, I mean, all the stuff that I'm going to write now, it will be superstrings. I will only be concerned with the bosonic part of that. But that's different than just bosonic. I mean, it will be. I mean, it's different than just bosonic string. There is extra bits of that. But I will do bosonic sector. So for the heterotext string, which I think has the same bosonic sector as the two as type 1 superstring. The fields of the theory, so the background of the string is formed by the same data as before. So the string is moving in some relatively rich background, but there is an extra piece, and that extra piece is a connection. Okay, so maybe just since I said we are working locally, so this thing can be seen as a one form valued in some Lie algebra. And my claim is again that you can again encode now it's these three guys as a generalized metric. So you have now somewhat more general bundle. So you have T plus T star plus T star M plus G, which has a structure group, I guess, O n plus dimension of G n. And if you reduce it down to the maximal compact, it should again correspond to okay, so let me draw the picture again. So now this is T and this is T star and plus G. And now again, it basically, what you're interested, okay, so it boils down to choosing a subspace of a suitable dimension, blah, blah. This is just a rough outline, so let me just skip the details. But okay, so this is subspace. It should have the same dimension as T, and blah blah blah. And again, you can see there's a graph of some map from T to this thing. But the map from T to here, it has two parts, right? Because it lands here and here. So the first part will give you G and B, and the map from T to G, that's precisely this connection here. Because it's that. So those three fields can again be written like that, and again you can show that the equations of motion, they just boil down to the same ones as you have here, and those will okay, I mean, this is pretty cool. Yep, please.
Can I ask a question?
Uh-huh.
What this structure group that I never seen that, so I believe it's true. But how come it's combining into that bigger ON? How come the G bit is not taken separately and having its own structure group just tensor together or multiplied together with ON? And
that's a very good question. Yes, so it's not just like that, because these two pieces, they kind of see each other. So for instance, you don't have the, if I remember correctly, like for instance, the H flux is not closed anymore, but it has to give you this, you know, some stuff built out of curvatures.
mm-hmm.
Right. So there is, I mean, those two bits are not independent, so they really need to be yeah, so it is really yeah, I mean, this is all just one organic piece. Actually, in more generality, and that's what I want to say now, in more generality, you should see these things as just transitive Courant algebroids. And that one, for that one, you don't have like a canonical splitting of this form. So there you cannot even say what G is precisely, I think, because there you will only get the, or am I wrong? Hopefully I'm not wrong. No, you cannot say, yeah, you can say what this is, because that's the kernel of the anchor, but yeah. So this was a lot about this stuff was developed in the works of Mario Garcia Fernandez. So I recommend that for, or we also mentioned something in our paper with Pavel about type II superstrings, which is basically the thing I was saying now. Okay, but anyway, so this was just, this is not the, yeah, so what is the main point of this talk is the remaining case of the superstring, and the type II case. So type II, which has two flavors. It can be type IIa or type IIb. And in that case, the string background, the massless fields, the bosonic massless fields are, again, you always have this triple. That's why some people call it the universal sector. And then, but then there is something interesting, which I will call F for the lack of, yeah, probably there is, anyway, I will call it F, not to be confused with the curvature of this A. And this F is a inhomogeneous differential form. So this is called Ramond fields. So Ramond, not just two times fields. Okay, sorry. So, and this thing, okay, so these things are, this is an inhomogeneous differential form on M, which is either purely of even or of odd degree. And this should be type A, and this is type, I mean, this would correspond to type IIa, and this corresponds to type IIb. And it has also the unfortunate property that it is self-dual, which makes writing down Lagrangian for it kind of more complicated. So, but anyway, still, I mean, this is what it is. And these are, I mean, for those who know, I mean, by those I mean really the curvatures for the Ramond fields. So if you want to take potentials, you need to go one form degree below. And so now a natural question is, can you do some crazy game like this also for type IIa and type IIb? I mean, it's the same game as before with this picture. And the answer is that in this context, not really, but you can do something different and very interesting. So, and that different interesting thing, it corresponds to saying that this thing here, these forms, that you can actually see them as spinors for the Courant algebroid. So okay, let me write it like this. So this thing is a space with an inner product, and so you can form a Clifford bundle, and then you can study the modules, and the natural spinor module is given precisely by this either even or odd things, and this even or odd, it translates to different chiralities of spinors. So there's like a very neat description of these things in terms of spinors, and also this condition here, it kind of lifts to a nice description here. So more concretely, you again encode these two guys on this guy. So you take again T plus T star, nothing else, just this one. So for those of you know, this is just the exact Courant algebra, so not transitive one, directly exact. And yeah, and so those two things you can encode as some sort of V plus, some reduction from ODD ONN to ON times ON. And then you can say what this Hodge star means. So what I'm saying is that you can cast all of these things into a more Courant language, which I will make more precise right now. Just final thing to say that the equations of motion now for these guys, you can again encapsulate them into saying that the generalized Ricci of V plus and phi. Okay, so these two guys again, they correspond to some V plus, is now something that contains there is some quadratic expression in these f's on the right hand side. And then you have the vanishing of the Ricci scalar. And so now the difference now with as opposed to the previous case is that in the previous case all these equations were nice homogeneous. It was just vanishing of one Ricci tensor or generalized Ricci tensor. In this case it's different. There is some right hand side, and in particular you cannot encode all the fields modulo the dilaton insert of one generalized metric. So that's oh yeah, sorry, I should also tell you what are the equations of motion for f. And so those ones, I think that's the most interesting part. Those are given by this condition. So there is a natural object. Okay, in this case it will be just closedness. Okay, it's just that they are closed, but let me write it in this funny way. But yeah, I just at this point it just means that they're closed.
What is that second equation of motion? The R1?
It's I think that's for phi, that's the vanishing of the scalar curvature.
I see.
Yeah, thank you. Right. So now to kind of encapsulate all this discussion up to this point, there is it seems very useful and simplifying if you instead of describing things in terms of normal geometry, you describe in terms of something like some extended tangent bundles. So you take either this T plus T star or T plus T star plus G, and it's just perfect, apart from the type 2 case where it's also perfect but in a different sense, and it doesn't fit the pattern really here, sort of, because you have right hand side and stuff. But the takeaway message from this part is that you can simplify things if you pass these other bundles. And so at this stage it's probably good to say that, okay, so like the idea behind is that there is an object called a Courant algebroid. So I believe most of you know very well what this is, but let me still says that, okay, so in general this is a structure which corresponds to, there is some data. So the data consists of a vector bundle. So this vector bundle in the pictures above was either T plus T star or T plus T star plus G. There is a structure group. Okay, so there is an inner product, which I will write in this funny way, that there is an OPQ structure group for some signature PQ. There is a bracket, which I actually didn't mention, okay, and I should have. So in all these cases, the way to construct these Riccis and generalized Riccis and everything, it kind of goes through the construction where there is a nice bracket on the sections of these things. So in this case, it would be just the commutator of vector fields. In this case, it's something more complicated and more interesting, and also is a natural bracket on these guys. Let me not be more explicit. But it's part of the definition of this algebroid that there is. I mean, that's the most important part of the definition. There is this bracket. And finally, there is some map, which is kind of implicit in the previous examples, and that is a map from E to Tm. This is called the anchor map, or the rancor map, because it's row. Okay. So yeah, in this case, it's just projection to Tm, in both cases. Now, yeah, so now an important observation is that there is a easy way how to determine if you are given a Courant algebroid, just a random one. It can be written in some sort of weird basis, frames, whatever. There is a nice way how to see if it is actually of this form, if it's of this form or of this form. And that is, so if you say that, okay, so actually, so claim, so if rho is surjective, then E is actually locally of this form, T plus T star M plus G. By the way, I should have maybe said that by this G, I really mean the trivial, the product bundle with just the Lie algebra. And yeah, and if rho is surjective, so special case, if rho is surjective and the rank of E is twice the dimension of the underlying manifold, then just looking at the previous line, this would just mean that this thing is not there, because this is already a rank of the dimension of M and the same as here. So this thing would imply that E is locally of this form. And the equivalent way to say these two conditions is to say that a certain natural sequence valid for any Courant algebroid is exact. So this is the same as saying that this is exact. Okay, so yeah, this is known from the works of Pavel Sugar. And yeah, of course, in the line here, I should have said that, okay, so since I apologize for being a little bit sketchy. So here I should have said that this is a definition that you have to have such structure such that some conditions are satisfied. Okay, so some conditions, yes, there's a Jacobi identity, etc. So some natural looking.
Can I have a question?
Yes, please.
So how do you get the which Lie algebra do you get depending on these axioms? How do they look like such that you get different type of Lie algebras?
Sorry, can do you mean this one here?
Yes.
So from this you cannot. I mean, any Lie algebra would do. Sorry, not any. You need to have it needs to have an invariant pairing. And then if you do that,
which one is it? I mean, the question is, if you have axioms, you wrote Jacobi ... What is ... such that you get which Lie algebra?
Sorry. Are you asking like which bracket does this refer to, or sorry? I think I don't understand the question.
So there's apparently some axiomatization for transitive Courant algebroids, but I suppose for that, I suppose if you just say that you take a Courant algebroid with surjective anchor, then this G is maybe a particular Lie algebra, right? No. It can be any quadratic Lie algebra, any Lie algebra with an invariant pairing. You can get so just from knowing it's transitive, you don't know. Any quadratic, I see. Yeah.
Any quadratic would do, yes.
Yeah, I see.
Yeah.
Okay.
Sorry, I okay. Right. So yes. So okay. So now why am I telling you about these Courant algebroids? So from the discussion above, it seems that, for instance, if you're interested in bosonic string, then you shouldn't care more than just about this guy, right? I mean, because this is a very, very particular case of a Courant algebroid. But the reason why we care about these more general things is that there is this thing called Poisson-Lie duality. And so let me say what that is. Poisson-Lie duality. And so it goes as follows. So suppose you have a Courant algebroid. So I will just write E over M. Okay, the other structures are kind of implicitly hidden. I mean, they're hidden. Well, they are also part of the definition, but let me just write E over M. And sometimes it may happen that you have a map like this. So you have some let's say surjective submersion into M. And if you have such a thing, then you can pull back the bundle and you get some bundle. Let's say call it E prime. So this is the pullback of that thing. And this was a Courant algebroid. This is so far just a vector bundle, but sometimes it's possible that you can equip this guy with a structure of a Courant algebroid, which is compatible with this pullback. So what does that mean? It means that, for instance, if you take two sections of this guy and you take the bracket, then and pull it back, is the same as if you would first pull them back and then take the bracket, and the same with the anchor map and the inner product. So so such a pair of Courant algebroids, we can call them compatible. So yeah, that's the definition of it, really. And now suppose that you have such a thing, but you have two of such guys. So you will have a different surjective submersion from some m double prime, and you pull it back, and then you equip this thing with a Courant algebroid structure. And suppose furthermore that these two Courant algebroids on the wings, this one and this one, are exact. For simplicity, they can be also transitive in the heterotic case, but okay, let me do exact. Okay, if they are exact, then the one in the middle is usually not exact. So, but anyway, so if you have such a setup, so such a pair, two pairs of compatible Courant algebroids, then you call the ones on the wings that they say that you can say that they are Poisson-Litty dual to each other. Obviously, you can have more. It's not necessary to stop with two dashes. You can have E triple dash and everything. So a more appropriate word would be to use the word plurality. But okay, a pair is enough for what I want to say. Now, the reason why this is interesting is that you can show that if you equip, for instance, if you put the generalized metric on this guy in the middle, and a dilaton or whatever, and then you pull it back to generalized metrics here and here, then this data will give you some string backgrounds, and those string backgrounds are equivalent in a way. So string moving in one is the same as string moving in the theory. Okay, there is various ways to say what this means, but you can say that the corresponding sigma models are equivalent, or you can say that.
How does this work with pulling back generalized metrics?
So generalized metric is if you see it as a structure, as a reduction of a structure group, then you can, since this is a pullback bundle, then that's just a pointwise, a fiberwise statement. So you just whenever you pull back something that has some reduced structure group, then you also pull it back. So that just goes very naturally. And with the dilaton, I didn't say what the dilaton was, but if you see it as a function, okay, let me not go into the dilaton issues. That one is
the functions you can just pull back, I guess, by
yes,
prime to m, no?
That's
easy. No, but if I view a generalized metric as a graph of some map, if E prime is bigger than E or something, I just wonder.
It's the same thing, because the picture carries over. This was a pointwise picture. So since the bundle is just a pullback,
usually you have some kind of non-degeneracy conditions, like this E plus and T plus T star needs to be non-degenerate. Now, if you have a bigger one, like
okay, so
what are even the conditions to say it's a generalized metric?
So in this case, there is no condition. This always works, and the reason is that this. Okay, so in the simplest case, this thing here is just something over a point. So some vector space actually with this structure, it actually becomes a Lie algebra. So let me use G maybe, and then this thing, it will be some manifold, and this thing here will be, well, since it's a pullback, it's really G times this one. But if I want that it is exact, then it's actually secretly T plus T star. So in particular, so what I'm saying is that this thing here, this is not T plus T star, because it's not exact. But here it is T plus T star. But in any case, what you are pulling back is just, I mean, you have just identification on the level.
In this case, I can imagine. But what happens if E is exact?
If E is exact, then the only way to have an exact pullback is to have an isomorph, an identity. So you cannot.
Okay.
This thing is not exact.
The issue. Okay, so okay, I see. Okay, thank you.
Yeah, thank you. Okay, very good. So, yeah. So, okay. So now the reason why I was telling you all this is that now that there is a nice strategy or a program which goes as follows. So you look at this, everything that I wrote in green here. So all these generalized Ricci tensors, curvatures, structure groups, spinors, some Dirac operators and stuff. And now you realize that all of this actually generalizes to an arbitrary setup. So it's not for instance, in this case where we really just work with T plus T star. Actually, these things, they make sense on arbitrary Courant algebra. This is a non-trivial statement. So this is kind of basically the result of this work that I mentioned before, that you can actually generalize all these objects to a general Courant algebra setup in a way that behaves naturally with respect to operations such as these pullbacks here. And having said that, this already implies that there is a sort of, this already is a kind of a powerful statement, because it tells you that if you have such dual pair of algebroids, then if one of them is, let's say, generalized Ricci flat, then the other one is as well. So there is kind of, because again, because these Ricci tensors, they behave naturally with respect to pullbacks. So if you put a generalized metric here such that it is generalized Ricci flat, then also if you put it here and if you put it here, they will also be, because Ricci is natural with respect to pullbacks. So all of this story, or all of this endeavor of working things more generally, not just for exact Courant algebroids, is useful for statements like this, for Poisson-Litty duality. And okay, and now I can tell you actually. So this was all this corresponds to the first part of the abstract, where I will just outline like what's the situation. And now the novelty here is that if I return to this type 2 case, then as you see here, things get more messy, because you have suddenly some right-hand side and stuff. So now the novelty, or the new beautiful story, comes from kind of rewriting this in a form that it really looks like the ones before. So I was talking about particles and strings. So now let me use this color. So let me talk about membranes. So, and here the observation is sort of as follows. So before, we had this structure group which was just GLN, and in this case we had ONN. So now I will proceed a little bit further, and I will take the exceptional group. So suppose that you take G to be okay. I will explain what this means. So this is R plus, and this thing, by this funny notation, just means that it's a split real form of the complex exceptional Lie algebra. So maybe you know from Dinkin diagrams that if you have, for instance, E7, E8, then they have Dinkin diagrams like this. This would be E7. No, this would be E8. No, 7. It's E7. And actually, for some reasons, I will only restrict here to some sort of special case when this n is smaller than 6, which sounds maybe funny if you haven't seen this before, but I will take from 3 to 6. And by this, I just mean that there is a way to really to kind of continue in the definition of these exceptional groups in terms of Dinkin diagrams. So for instance, if you would, this would be E7, this would be E6, right? This is the standard notation. But when I say E5, I really mean just remove one more node, and you end up with this thing. And this thing is nothing else than just, this is SO10. Or if you take the split real form, it's SO5, 5. So let's see, the algebra E and N. If you take n equals 6, then this is just E6, 6. Nothing to say about that. If it's 5, then it actually coincides with SO5, 5. If you remove one more node, then this is just SL5. 4. If you remove one more, then this is a no longer simple. So this is SL2 plus SL3. Okay, SL2. Sorry, SL2 plus SL3. And yeah, and I will stop here. I will not go beyond. So these are the objects that that we will take, and just as before, these bundles they corresponded to some specific representations of these groups. So for instance, this thing was just a vector representation of GLN. This thing here was just again a vector representation of ONN. In this case, I will also need some representation, and let me just tell you that in all cases, in all these Dinkin diagram cases, I will always take I will always take the representation here. Let me call it R1, which is or the leftmost node. So for instance, for SL5, it would be this one, and that would correspond to two forms if you know the representation theory. And I will call, okay, let me not call it R1, let me call it E, which might be a little bit confusing, but we will get there. So this is E, and there will be another representation which will be very important for us, and that taken to be the one which is on the rightmost tail here. So that one I will call it N. So stuff to remember at this point is just that there is some group, exceptional group, and there is some two specific representations, and they have some important property. This N actually can be seen as sitting inside the second symmetric power of E. Okay, so these are the only things to remember at this point. And yeah, okay, let me switch to a new page. No, okay. This one. Okay, so now the underlying idea behind what I'm going to behind this kind of membrane picture is that again I will take some bundles which correspond to this representation, and I will take the structure group of that to be this G, so this exceptional group roughly, and I will now take the fields to correspond to the structure group from that to the maximal compact subgroup of thereof. Okay, so my claim is that this precise such a structure group again encodes the fields, the relevant fields of the theory. This I mean this is not, this was known. This you can see if you go back to the works of Chris Hull, Waldram and Pacheco, Waldram, Strickland Constable, and Coimbra, and maybe others. So the claim is that if you now take a reduction from G to the maximal compact subgroup of that, so maximal compact, there is not a unique, I mean, all of them have different maximal compact. Here you get SO5, here you get SO5, SO5 times SO5. In this case, you get SP4, the maximal compact ones. But in all the cases, it turns out, and that's the interesting thing, that the fields they just correspond to reduction from this to its maximal compact. So this is kind of the amazing thing here. And not just that, but also you can encode the equations of motion in terms of some suitable Ricci tensor. Okay, so I see that I'm getting towards the end, so let me just give you maybe the new, well, the definition at least. So I will now need some object which replaces Courant algebroids, and I will call it exceptional algebroids. Exceptional algebroids. Or shortly just Elgebroid. We actually use that word in the article. It's shorter. And okay, and so this thing by definition, if we look back at the definition of Courant algebroid, then it was a bunch of structures. So this carries over. So here, this is given by a vector bundle, a structure group. So in this case, I'm sorry, you choose a G structure on it. And furthermore, and sorry for being sloppy, I want that this E, it transforms in a particular representation of G, and namely in this one. So that's why I call this one here E. Okay, so that's a little bit of an abuse of notation, but I mean, we wanted to that this generalized tangent bundle transformed it as in the vector representation of the orthogonal group. In this case, we want that it transforms in this E representation. So that's kind of hidden in this notation. Okay, so you want that, you want to have some bracket, you want to have some anchor map, which goes from here to TM. And one technical addition here, we want one more thing, and that thing would be to map a linear operator, R linear operator, which goes from sections of N to sections of E. Okay, so sections of E, that's clear what it means. And sections of N, I mean that once you have this G structure on this guy, you can kind of form associated vector bundles. So you also have an associated bundle to this representation, and I will just call it N. Okay, so here N is meant to be a bundle corresponding to this N. Okay, and such that some axioms, such that some conditions, and at this stage probably I will write them so that at least I can say that I did something explicitly. So first and foremost, you have the Jacobi identity. Which is written in this form. I mean, this is the natural form, kind of. You want to say that the bracket is a derivation of itself. Yeah. Furthermore, you want that if you put a function. So in this notation, A, B, C are sections of P. Okay, the bracket is an ordinary operator on these sections. And if you put some function in front, then you want that this thing has some sort of prescribed behavior. So you know that this thing is given by. So there is a term which acts as a derivative on F, and that one is given precisely using the anchor map. That's why the anchor map. That's what the anchor map is for, kind of, to do this. So such a structure satisfying this one line, this is called a Leibniz algebroid, but we want more. So we want also that the symmetric part is not arbitrary, but it has some specific form. And what form? So we want that in the Courant algebroid, if I would write the axioms about, then the corresponding axiom would be that you need to take the inner product of those two things and then do something with it. So in this case, there is no inner product, but you can take the tensor product of these two things and then project it down to N. Okay, so remember that N was inside second symmetric power of E. So if you have two guys, you can, there is a map to that. So you take a projection map, and then this is a section of N, and now you can apply this D. Okay, so that's the axiom, and now you still don't know what kind of linearity we have in the first. Oh, I see my connection is unstable. Can you hear me? Okay, good. Thanks. So this thing still doesn't tell you what happens if I would put a function in the first slot, because for that we would need to know how this thing behaves with respect to functions. So that's the other axiom. So if you have some section of N of the N bundle, let me call it just N, small n, and you multiply it by a function, then you want that this thing is not tensorial, but it has a part which, okay, now this is a slightly nasty thing to write, but okay, so you want that there is also a derivative part on F. So you want that there is a df, but now you want to have something in E, right? I mean, because both sides are in E. So how to make something in E? So you apply the transpose of the anchor map. Okay, so anchor map goes from here to here. So the transpose goes from T star M to E star. Okay, so this result is in E star, which would be all good for Courant algebra, but in this case we cannot go from E star to E, but we still have this N here. So you can tensor this with N. Okay, so this thing here is a section of E star, this thing is a section of N. And now if you write this map down, so yeah, N is embedded inside these guys. So there is a map from N to E tensor E. So if you take the partial dual of that, you get a map from N tensor E star to E. And that's what we use here. So I will just put a parenthesis and say that project this to E. The upshot is that there is a precise formula for that. Its precise form is not that important, but there is a formula. Okay, and finally, you want to have some compatibility with the G structure. So let me just say that the bracket with any section preserves the G structure. Yeah, okay, let me just stick to that. I mean, there is I can make this more precise, but at this stage, let me just say it like this.
Well, I would like to know more precisely what it is.
Okay. So if you have any, okay, so there is a quick way and there is a nice way. So the quick way would be just that if you have a G structure, it means that you have a set of preferred frames, and if you have a set of preferred frames, let's call them EA, then this condition, or E alpha, then this condition will tell you that if you take a bracket of that and modify infinitesimally this frame, that this is again a G frame. I think that's probably one way of saying that. But a nicer way to say that, what the thing is that whenever you have a Leibniz algebroid, so whenever you have something in the first line, then then any section induces a vector field on the total space of the bundle, and in particular, it also induces a vector field on the frame bundle, and you want that vector field preserves the G structure, so the subbundle of the.
I see. Thank you.
Right. So, but eventually, for Courant algebroid, the important point is that for Courant algebroid, this reduces down to the known compatibility between inner product and the bracket. But in this more general setup, this is the only way how to say that precisely. And okay, and so the end of the definition. And now, a simple consequence of these axioms, which I'm not going to derive, is that you have a natural sequence again. So there exists a sequence which looks like, of course, looks like this. I should perhaps say that if you want to see more closely the correspondence with Courant algebroids, then for Courant algebroids, this N bundle is also there, but there it's just a trivial line bundle. The product line, so this is just R. The representation corresponding is just one-dimensional. So in this case, you just get T star M for Courant. In this case, you get something more complicated. But again, you can make a definition and say that this is exact. So you can say that the exceptional algebroids of E is exact if, this is the definition, if this sequence is exact. So that sequence is exact. And now kind of the crucial point is that there is a theorem which we proved. So this is Valach theorem, that those guys, just as Pavel proved for Courant algebroids, that the exact ones, they take some specific form. And there is a similar statement here, but here I will be just local. So it seems that because the global issues here are more complex than for Courant. So the claim is that if E is exact, then locally there is two possibilities. So one possibility is that if the dimension of M, so of the base manifold, is N, so in this whole section N is fixed. Okay, so N is a fixed number from between 3 and 6. So in this very wide range of values. The other option is that it's N minus 1 dimensional. And in each of these cases, you can show that locally there is a canonical form of this bundle, and it is okay. I can write what it is, but the message to take away is that there is just like a canonical form of this thing locally. And so in this case, for instance, it would be, in this case, you can show that you recover these bundles that people use in the context of exceptional generalized geometry. So you have this one plus wedge 5t star. I mean, to prove that the bundle is of this form, that's easy. That's just some group decomposition. But to prove that the bracket also takes a unique form, that one is more tricky. So that's the real content of the theorem. So there is, again, in order not to be very confusing, I mean, there is a natural bracket on this thing, which was studied by the guys I mentioned before, so like Waldram and collaborators. And the claim of this theorem is that that's kind of the locally. And in this case, it's more, this is, okay, let me just recall. This is Tm plus T star M plus T star M plus wedge 3 T star M. Okay, let me drop the M. Okay, so wedge 3 T star plus wedge 5 T star plus wedge 5 T star. And this thing here is the answer to the question at the beginning. So this thing here is the one that encodes the T plus T star, so the exact Courant algebroid, and also it has these weird odd forms. So 1 form, 3 form, 5 form, and okay, there is some tail, which has to be there for some reason, but okay, whatever. So this thing here is related to type 2B string theory. And this thing here is related to M theory. And what I mean by that is that if you take M theory or 2B string, you take the low energy limit, and then you compactify the result.
What's the small n, by the way?
This one, n?
Yes.
Oh, that's the rank of the exceptional group here. That's the parameter. It can be, okay. Yeah.
Okay.
So, yeah, so again, sorry, just yes, okay, so yeah, you take M theory or type 2B string theory, you take the low energy limit and you compactify that to get some theory in lower amount of dimensions. So that's these guys here. So it has relatively low dimension, and then you look at the then the structure that appears in that supergravity, the symmetries of the field content and everything can be described in terms of these algebroids. So as I mentioned before, if you now these guys, since they lie in the representation E, so that means that if you now choose the reduction of the structure of these guys to the maximal compact one, this will correspond precisely to the fields of theory. And there is again a Ricci tensor or some curvature tensors that you can construct for these guys in the fashion precisely analogous to Courant algebroids. And you can show that vanishing of the tensor is precisely the equations of motion of the theory. So in this case, this fulfills the dream of this section here, that this didn't look very homogeneous, well, very much like the previous one, but in this case it kind of does. But I should say that, okay, this by itself is not a known thing. What is known thing what was the new thing that we I mean, it's not new that the type 2B string can be written in this form. So this is already in the verse of Waldram and collaborators or Friesau. But the thing which we did was that we actually, okay, so first of all, we casted into this more general framework of exceptional algebroid and provided a nice condition under which you can determine abstractly that it has to be of this physically relevant form. But then also, because all the notions of curvature tensors and everything, it kind of extends naturally to this more general exceptional algebroid setup. This by itself again automatically sounds about Poisson-Lie dualities. So that's just a corollary of all this formalism, that now you can formulate something which is known, some recent thing which is known as Poisson-Lie U duality, and it's precisely the same thing in terms of this. It's the same picture. So you would have just this thing, but not Courant, but exceptional algebroids. So if you have such a setup of compatible exceptional algebroids, then again you can say that this and these are exact, and that's precisely what people defined as Poisson-Lie U duality recently. And furthermore, you can show that this you can also search for solutions to equations of motion, because if you want to have like a thing which satisfies the equations of motions, it's kind of reasonable to start with this guy here and solve the equations there and then put it back and stuff like this. So the goal of our work was to put this in the framework of Poisson, so formulate Poisson-Lie U duality and prove some statements about consistent truncations, which I could say go on for like maybe 4 more minutes, but I don't want to really exceed the time. Sorry. So I think already there was supposed to be time for questions. So let me finish at this point, and thank you very much for your attention.
We thank to the Fritzl for his very nice talk. And yeah, as he said, I suggest people to ask questions or remarks.
Maybe I can make a remark. I just see the structure the first time what you wrote, but it reminds me a little bit of this vector bundle twisted Courant algebroids, which we long ago defined with Melcher-Brützmann. And the funny thing is, there was also an exact sequence which just had precisely the same form. And if the vector bundle n was of rank bigger than 1, this was equivalent to lead to algebroids. Just mention it, and maybe next week when you come, we can look together.
Yeah, no, I would be delighted. Yeah,
to see
I know
how it's
about
related in more precisely.
I know about that work, and I want to look at it more closely. So I would be very happy to discuss
I don't know,
that.
but at least there are some things which are similar.
Thank you.
Fritz, may I ask you what about the 2A?
Yes, I didn't say that. Very good. Yes. So thank you for the question. So 2A is a work in progress, but I can tell you what the result is. So the result, or what the expected result is. So the what's the best way to say that? So yes. So okay. So this claim for okay, so 2A corresponds to a case which is not exact, it's transitive, but it's kind of almost exact. So there's like one-dimensional discrepancy in the sequence. So that would correspond to have, okay, so exact would correspond to having, if I remember correctly, that you still want exactness in this piece, which means that you want the anchor to be surjective, so it's a transitive exceptional algebroid. But this thing, right? So do we want that? I think one way to say this, you wanted the kernel of this map. So this is rho. So you wanted the kernel of rho to be what we call coisotropic, but you don't want it to be co-Lagrangian. So so there is a notion of a subspace being coisotropic, which is it's all in terms of these structure maps. So you say that the subspace V of E is coisotropic if you take its annihilator. So this is something that lives in the dual, and you take it twice. So this is inside E star, and then you project it down to N star. Okay, so because this thing basically tells you that you have a map from like this. So dually you have a map from E star to N star. So if you project this down to N star, you want this to be 0. In such a case, you would say that the subspace is coisotropic. Oops. So in a particular case of Courant algebroids where this N was just R, and this map was just inner product, and it really coincides with the coisotropicity condition. In this case, it's more or something more general. I mean, different. So there is a notion of of a subspace being coisotropic, and you can have, there is an interesting structure of coisotropic subspaces, and you can have a minimally coisotropic one. So subspace is minimally coisotropic if it has no proper coisotropic subspace, and it's already coisotropic. And it turns out, and that's the kind of different thing here as opposed to Courant algebroids, that here there is not a unique, there is not just like one. I mean, there is two options. The co-Lagrangian subspaces, so the minimally coisotropic subspaces, they can have two different dimensions. They can have dimension either or codimension either n or n-1. So that's precisely this fork here, that you have these two cases. So yeah, and so what I'm saying is that there is, if you write down the structure of what are the possible co-Lagrangian or coisotropic subspaces, then it has an interesting kind of forky structure. So there is two possible minimal ones which correspond to this M theory and 2B string, and then there is one which is kind of not minimal. So there is a there exists a non-minimal coisotropic subspace dimension n-1. So to return to your question, so 2A would correspond to, I could make here, so if E is not exact, but if, let's say, rho is transitive, it's transitive exceptional algebroid, and the kernel of rho is inside E is coisotropic, but not co-Lagrangian, so not minimally coisotropic, and of codimension n. Okay, so there, I mean, it's kind of okay, probably there is better, well, less words to describe this, but you need to go to transitive ones. It's like you need to go one little step beyond, and all of this is just a consequence of the fact that in string theory you have type 2a string theory can be seen as a reduction of M theory. So that's why you take M theory, compactify it on a circle, and then you get, I mean, you reduce it down and you get 2a. So it's kind of not really, there is something beyond it. So that's why it's not kind of minimal Lagrangian. But okay, maybe I should not write this. I mean, it's maybe confusing, but it's like that, but you have to relax the exactness. It's kind of having a heterotic thing, sort of, in this case. Heterotic, but because these heterotic things correspond to transitive Courant algebroids. So it's something similar, but it's kind of like minimally heterotic or something like this. Okay, I hopefully this was not totally confusing.
No, thank you.
No, thank you for the question. That is actually a good point because I didn't talk about 2a at all. Yeah, but this actually shows that these 2a and 2b are very different from this perspective. In the perspective of Courant algebroid, they were really, I mean, it was just like you switch to chirality. In this case, it's really like the whole story changes. Sometimes it's, I mean, it's interesting. And in that case, actually, the result that we have is that you don't have a unique form locally. So that's maybe something that I should say. It seems that you have there is a small choice of things, basically corresponding to the fact that one of the fluxes that you have is scalar, or one or more fluxes that you have are scalar, and scalar fluxes are difficult to twist away using gauge transformations. So there is something that you can, I mean, more complications and more interesting stuff happens in 2a, is what I'm saying. Thank you. Hopefully that answered some.
Yeah.
Okay, I noticed some question in the chat. So
oh yeah,
I don't know whether it has been answered.
I will read it. I didn't look see it. Sorry, I will.
Yeah. From Yanchi, taking M to be the point shows that any quadratic Lie algebra is possible, as the anchor mapped to zero-dimensional vector space will be surjective then. So it's a comment.
No, I think this was for Thomas. Sorry, yeah, this was. Sorry, this was an answer to Thomas's question.
Okay. Maybe I would have one question. Maybe I didn't get the crucial point, but is there any suggestion for a generalized Ricci tensor? Or...
Yes, there is a natural generalized Ricci tensor in this context. It was not the most exciting part of the work, so we didn't stress it that much. But there is a natural way. So it goes by. So first you have to show that there exist torsion-free connections. So if you, for instance, if you go to one of these bundles with this structure group and blah blah blah, you have to do some generalized connections. You can show that there exist torsion-free versions of those, and then there is a nice play. There is a choice of other representations other than this E and N, and if you play with them a little bit, there is a sort of groupish, algebraish argument that you can form a tensor at the end, something that like where non-tensorial parts fall out. But in this case, it's more complicated. You really have to do some group theory. Yeah. But you can eventually construct. There is a Ricci tensor, and its vanishing should encode the equations of. Yeah. Or if not Ricci, then there is some generalized curvature tensors.
Did you check that it boils down to the Courant case as a special one, or?
No. And the reason for that is that the reason that I didn't check is that it was known that the Ricci tensor exists. So Waldram and collaborators they constructed this tensor for these bundles. So all we needed was to kind of just go one step and actually show that. And this was actually not the difficult part. That's why I didn't stress it here. But you can show that it extends to an arbitrary exceptional algebroid in a way that is compatible with these kinds of pullbacks. So to do the check that you say, we don't have to do that because it was already done by these people. We just kind of extended it to a more general setup, realized that now it works for this Poisson U duality, and also we apply this to consistent truncations. I think that's actually the most interesting part, but yeah.
So is there any other questions? Seemingly not now. So we thank the speaker again.
Thank you. Thank you very much for